Right. I think I'm clearly audible now. So, if you are having, as I mentioned in the earlier sessions as well, so we'll start, okay? And if you are having any sort of question or anything related to this stuff, you can use the chat box. Or now you can use the microphone to ask the answer questions, okay? So I'm using a wired headset here, so you can easily ask the questions here. So today we'll discuss about the third unit here, chemistry. Uh, the physical chemistry part. So this will be like we won't be taking much more time here. So which means like I'm not going to discuss more about the calculations and all the related stuff. Here I'm just just revising all the theory parts that you need, right? Just refreshing your memory. So it's your duty to go through the question tunes and all the past paper questions related to this. So once you finish this session within today, try to complete the past paper categorized that tutorial, right? Complete means like once again go through it and see whether what are the questions that you got wrong. Okay, right. So here, when it comes to physical chemistry, so physical chemistry is actually a wide study field, and here in your level we will be just discussing about small stuff related to energetics and also some basic theory parts related to equilibrium, right? Okay, so here just a basic thing is given here. So in this discussion we will be focusing on the energetics part, which is focusing on the energy related to bond making and bond breaking. And then we will be discussing about the chemical kinetics. So here we will be just discussing about the basic theory parts and all the related stuff. And finally, we will be discussing about some equilibrium related stuff, right? So remember, we are just laying the foundation for the A-level chemistry part here actually, right? But once you are facing the A-level chemistry, physical chemistry section. So we will be going much more deeper than this, right? Okay, so then here we will be discussing, as I mentioned, we will be discussing about chemical kinetics and also the energy, the chemical energetics and also then the equilibrium part, right? So first of all, we need to get an idea what is exothermic and what is endothermic. So exo means you are emitting, right? You are releasing, right? Exo means releasing. So releasing thermal energy, right? Releasing thermal energy. Or you can say heat energy, right? Here, endo means you are taking, right? You are taking in or you will be receiving thermal energy, right? Receiving thermal energy. So transfers energy to surroundings, which means emitting, releasing. So therefore, the temperature increases, right? So therefore, the temperature increases. So remember that part. The reason is like there were so many questions related to these exothermic and endothermic reactions where we will be focusing on that thermometer thing, right? So in those calculations, you might have seen that. So the starting temperature is somewhere around 20, and once after the reaction is done, now the temperature becomes 35 Celsius, right? Becomes 35 Celsius. So therefore, they are asking whether this reaction is exothermic or endothermic. So you can see the temperature has gone up. So therefore, this is going to be an exothermic reaction. So just imagine in another case, so we'll say the starting temperature is 35 Celsius and the temperature dropped to 30 Celsius. So the temperature dropped. So which means the energy has been absorbed from the system to the object, right? From the system to the object. So therefore the temperature decrease. So therefore it will be falling under endothermic. So it takes energy from surroundings. So therefore temperature decreases. So remember those points, right? Then there are some examples given: combustion, oxidation, neutralization, self-heating, cancer. Okay. Then for the endothermic reactions, thermal decomposition, sodium citric acid plus sodium hydrogen carbon, which means like yeah. So here citric acid and sodium hydrogen. No need of remembering the exact examples, right? Just remember one or two. And here, this sort of a thing is known as the energy graph or energy diagram, right? Energy profile. Energy profile, right? So here in exothermic, you need to release energy. So from this part, the energy will be released, will be given out, right? So which means the reactants will pack higher amount of energy than the products. But in the other case, so always reactants to products, that is the pathway, right? So in order to convert reactants into products, you need to give energy, right? So you need to give energy. So therefore, the energy profile for endothermic will be like this, right? So remember these points. Then the net energy of a reaction is a strict accounting of bond, broken, and the formed bonds, right? So first one, we need to provide energy, then the bonds will be broken, right? Then the bonds will be broken, then new bonds will be formed. So when it comes to that, right, it is better to remember this equation. So yeah, in the theory classes as well, I have given these equations, right? So the total enthalpy change of a reaction will be equal to sum of bond energies, right? Which means the amount that we need to provide, right? Or you can say sum of all the bonds, right? Sum of all the bonds that we are having, right? Sum of all the bonds that we are having minus bonds, we can say here, bonds must be broken, right? Sum of all the energies of the bonds must be broken. And here it will be sum of all the bonds to be formed. Sum of all the bonds that is to be formed. For example, let's say something like this, right? So our reaction will say, okay. So our reaction, let's say CH4 gas, right? So always remember we are dealing with the gaseous components here. CH4 gas reacting with oxygen, which means burning here. And you will be getting carbon dioxide and water, liquid. So you need to, first of all, balance the reaction. So if we balance the reaction, you can see here just one carbon atom and here also just one carbon atom and four hydrogen atoms. So here, in order to get four hydrogen atoms, you need to put number two there, right? And so this the right hand side is already balanced. So if we calculate about the total number of oxygen atoms, here you can see it is going to be 2 plus 2, which means 4. So therefore, here also going to be 2, right? Now, once again, check the numbers. So the numbers are correct, right? So when we are dealing with the bond energies, right, you need to focus on the structures, right, about the bonds. So in your level, there's no need of remembering the bond structures or something like that. But just looking at the diagram, you can get it. Just looking at the reaction, actually, right? But in most of the cases, in the calculations, they will give the structures as well, right? They will give the structures as well. So here, if we consider about CH4, it will be having a structure like this. And for oxygen, a double bond, right? And here we are dealing with two oxygen molecules. Then carbon dioxide, it is going to be having a structure like this, and water going to be something like this. And also, we are dealing with two water molecules. So our equation is that, right? The bond, sorry, the total energy, right? Total energy is going to be equal to sum of all the bonds to be broken minus sum of all the bonds that are formed, right? Which means just you need to get this side, right? All the bonds in this side. Right. So now we can write an equation here, right? So the total energy is going to be equal to, so here you can see, right? If we are going to break the CH4 molecule, then you need to break CH bonds, right? You need to break CH bonds. So here you are having four CH bonds. So which means you need to break CH bonds, but there are four of them, right? There are four of them. Plus, here you're having oxygen-oxygen double bond, right? Oxygen-oxygen double bond. And also you need to multiply it by 2 because we are dealing with two molecules there. So this is the summation of all the bonds that is to be broken minus all the bonds that are to be formed, right? So here you can see CO double bond, right? CO double bond, and actually there are two bonds of them, right? So CO double bond and two of them plus OH bond, right? OH bond. So one molecule packs two, right? OH bonds. One molecule packs two, but we are dealing with two water molecules. So therefore, altogether, how many OH bonds? It will be four OH bonds, right? So this is the total that is to be formed. So then you can apply the data points and get an answer here, right? And get an answer here, right? So always follow the steps, right? There are no any shortcuts. Always you need to follow the steps. Once you are get fluent in these type of calculations, then you can just see the diagram and get an answer. Just see the equation or the reaction and get an answer, right? But for you guys, it's better to follow all the steps. So all the steps means like first one, this thing, you need to figure out all the bonds, right? And then the second one, reaction and applying the data points. So here, if we consider about the C or double bonds here, right? Okay. So here, if it is like this, right? The question is, you are dealing with C or double bond, right? Not just CO bond, right? Normally, we cannot have these type of bonds with oxygen. So definitely, if there are oxygens, then there must be two bonds, whether it is going to be something like this or like this, right? So these are no need here, right? But here we are dealing with carbon dioxide. So each carbon dioxide having, this is just one, right? This is just one, and the other one is this. So in the data booklet or in the question itself, they will give these bonds and their respective uh, breaking energies, right? Their respective breaking energies. Then you can easily figure out that thing. Okay. And for this thing, so each molecule packs two of them. So we are dealing with two molecules. So therefore, altogether, four OH bonds. Altogether, four OH bonds. And here there are CH bonds altogether, four of them. Altogether, four of them. Likewise, you need to analyze it, right? So it's better to go through those calculations. These are actually easy calculations, right? So once the session is done, just take 30 minutes or 40 minutes, just quickly revise through the calculations or those specific tutorials which I have given, right? So then you can easily uh, go through the calculations, okay? Then the collision theory and kinetic related stuff, right? The reaction rate control, reaction rate means the speed of a reaction, right? Control panel allows chemists to manipulate collision frequency. So this manipulation thing, right? So it will be used in chemical industries. So when it comes to chemical industries, so industrial level means we need to pay more attention to the revenue, right? So the income, right? Not actually the income, the revenue part, the profit that we are focusing on, right? So that is the main difference between an laboratory experiment and the industrial experiment. So in laboratory experiments, we just use a small sample, we produce a small sample to check their properties or to develop a method or something like that, right? Properties. So just to identify the stuff. But when it comes to the industrial level, we will be producing them in mass scale, right? The reason we are focusing on profit. We are focusing on the profit, right? We are focusing on profit. So in industrial scales, we need to have a huge amount of product. So we need to, we need to drive the reaction in order to have a higher product value, right? So which means we need to manipulate these reactions in order to have a higher speed. So that is the main reason we are using these reaction collision frequencies and reaction rate related theories in the chemical industry. So the first one is the temperature, right? The temperature. So here, the final summarized thing is given here, increases particle speed and collision energy. So, but in classes, I have given you the specific way of writing these things, having 5 sentences there, right? So better to write that one, just not just the final part here, right? Then the surface area, and in the class also we discussed about how the surface area when the product, sorry, when the reactant becomes in granular form, or we can say some small particles. So when you're having small particles, the volume doesn't change, but the surface area changes. So surface area changes means the the reaction surface, right? The reaction surface itself increases. So therefore, you can have more collisions with them. So therefore, the second one, surface area of the reactants increases the reaction space for solids, right? Then uh, the concentration or the pressure. So concentration or the pressure. So if we increase the pressure, right, the crowding of the solution or the reacting gases, right? So they are packed together. So which means more and more particles will be collided. So you need to formulate your answer according to that. Okay. So fine. In the classes we discussed about these things. And when it comes to catalysts, right? So this is the third one, concentration or the pressure, and the fourth one is the catalyst. So these are chemical substances that we use to speed up the reaction, right? So speeds up the reaction chemically without being consumed. So these are some characters of catalyst. We have already discussed about these things, right? Then here the units and all the stuff given, so you can go through them. I'll upload this tutorial there, right? And the same thing is being explained here, right? So initially you are having few successful collisions, but if you increase the collision frequency, then you will be having more and more uh, collisions with the particles. So therefore the reaction will increase, right? The reaction rate will increase. And so according to what they are asking, you need to write the answer accordingly, right? So if it is concentration and the pressure and surface area increases, then you need to say the high crowding or more packed nature, right? More packed nature will allow more frequent collisions. And if it is temperature, then definitely, right? If it is temperature, then definitely you need to mention about the particle speeds, right? So remember that point, how the reaction rate changes. So if you are focusing on the concentration, pressure, or the surface area, so it will be increasing the collision frequency by allowing more and more collision spaces or something like that. But in increasing energy part, which means increasing the temperature, right? Increasing the temperature, so it will increase the kinetic energy. So when the kinetic energy increases, what will happen? Their speed increases. So therefore, when the speed increases, there will be more collisions, right? So here we are not dealing with more and more particles packed in this space or something like that, right? So there's a clear difference between these two. So remember that, right? So this is the most important part here, right? So remember how you are going to write the exact correct answer according to the question that they ask you, right? Remember those points. And this diagram is much more important, right? So catalysts They do not add energy. They build a tunnel through the activation barrier, or just don't use the tunnel term. You need to give an answer something like they are making an alternative route, or they are giving an alternative route, skipping the activation energy barrier, right? And also another important part, right? So remember this point, right? So most of the questions they are asking you to draw the activation energy, or label the activation energy. So always remember, if it is activation energy, then you need to start from the reactant level, right? That is the most crucial point. Remember, you need to start from the activation energy at the reactants level, right? It doesn't matter whether the reactants are here. Again, you are starting from the reactants level, right? So remember that point. So this value is corresponding for the activation energy. So here, high activation energy required. So this is without the catalyst. Without the catalyst, right? Once you add the catalyst, what will happen? It will, like, we cannot say actually it will lower the activation energy. That is not wrong, right? That is wrong actually. That is wrong. Sorry, that is wrong. So normally the reaction does not get affected by the uh, catalysts, right? So the thing that they are doing is they just provide an alternative path having a low activation energy. So this is the correct way of writing it, right? Provides an alternative path with a lower activation energy. So in this case also, see, the activation energy is measured from the reactance level, right? Reactance level. And let's say something like this. So, so this reaction is for an exothermic reaction. So if it is for a, let's say, endothermic reaction, for an endothermic reaction, right? Then you have energy here, and then this is the reaction pathway, right? So if it is for a, let's say, so the previous one was for exothermic reaction, and if it is for an endothermic, right? Endothermic, which means it requires energy, right? It requires energy. So therefore, reactance level will be here, and the products will be here, and the products will be here, right? So we'll just draw a diagram. So the path might be something like this. Okay, right, like this. So if they are asking you to draw the, let's say, activation energy, so once again, you are starting from the reactance level, right? So this is the reactance level, starting from the reactance level and to the peak, right? So this is the activation energy. Okay, remember that always starting from the reactance level. Doesn't matter whether the reaction is exothermic or endothermic, you are starting the arrow with the reactance level and to the peak, right? And to the peak. And just imagine, so now we let's say we introduced a catalyst into the system. So the reaction pathway might be changed to something like this. So if they are asking again the reaction, we'll say the activation energy. So still again, right? You are starting from the reactance level and to the peak level, right? So this is the new activation energy, right? Activation energy after adding catalyst, after adding catalyst, right? So remember the point. This is the important fact, right? So I have seen this thing, like I have seen students struggling in order to, like, find the correct place to start the arrow, right? So remember that doesn't matter whether the reaction is exothermic or endothermic. When you are drawing the activation energy arrow, you are definitely starting from the base level. Base level means starting from the reactance level, right? Starting from the reactance level. So remember that point. Okay. Then the next one, the reversibility, right? The reversibility of a reaction, right? So reversibility means, like, you can change any product into the reactants, and also in the meantime, the reactants can be changed to products as well, right? So no need of going through these diagrams, just grab the base idea there, right? And here there are some yeah. So as in this diagram, so the same thing, right? So I'll explain it like this. So just imagine there's a reaction A plus B, and the reversible reaction producing and C and B, right? So this reaction from left to right, this is known as the forward reaction, and this is known as the backward reaction or the reverse reaction, right? Reverse or backward reaction, right? So when it comes to equilibrium, right? Equilibrium, which means, right? At dynamic equilibrium, actually, right? At dynamic equilibrium, what happens is that the rate of forward reaction will be equal to the rate of backward reaction, right? Rate of forward reaction will be equal to the rate of backward reaction, which means the speed of the forward arrow will be equal to the speed of the backward arrow, which means the same speed where we are using A and B will be equal to the same speed where C and D are being used, right? So the concentrations might change. The idea that you need to get is the rate, the speed will be equal to each other, right? The speed will be equal to each other, right? Then here some of the important theory parts here given, but remember, so this theory is actually mentioned as Le-Chatelier's principle, but in your syllabus, in your exam papers, just don't write it as the Le-Chatelier's principle, because the term is not given there, and even in classes uh, we are not teaching it, but in LL classes, you need to deal with it. Okay. So if they ask something like this, so I will explain it. So it's another page here. Right. So this is what happens. So when it comes to Le Chatelier's principle, right? So it says, right? It says if there's an external, if there's an external effect, external effect, right? External effect on the system, on the equilibrium system, right? There must be an external effect, right? External effect on the equilibrium system. So the system, right? So the system, it tries to minimize that effect, minimize that effect by counteracting, right? By counteracting. So this is the most important part. The system tries to minimize it, right? So 100% it cannot, 100% it cannot destroy that, or that cannot, yeah, it will try to minimize, okay? It will try to minimize. Most of the time it will like, somehow manage to reduce the effect, but most of the time it will be trying to minimize it, not 100%, by counteracting. So that is the most important part that you need to remember. So counteracting means, so there are so many counteracting theories, right? So let's say, for example, I'm going to increase the temperature. So this is the external effect. So which means the counteract will be the system will try to decrease the temperature. So in the other way around also, right? So if I decrease the temperature, right? If I decrease the temperature, so the system will try to increase the temperature. So for, let's say, a concentration thing, right? So if I increase the concentration of a certain molecule, a certain substance, then it will try to decrease the concentration, right? And let's say I'm going to increase the pressure, then it will try to decrease the pressure as well, right? It will try to decrease the pressure as well, right? So here I'll say something like this, right? Let's say the first effect, the concentration effect, right? Changes, concentration changes. So I'll take A plus B forming C plus D, right? So at equilibrium, what will happen? Forward reaction rate will be equal to backward reaction rate, right? So which means, yeah, that's enough. No need of the graphs or anything like that. Okay. Then just imagine now I am adding extra amounts of, right? Extra amounts of A into the system, right? I am adding extra amount of A. So therefore, what will happen? The concentration of A will increase, right? The concentration of A will increase. So therefore, the system, it tries to decrease the concentration of A, right? It tries to decrease the concentration of A. So in order to decrease the concentration of A, then A must be, right? Then A must be acting as a reactant, right? In order to decrease the concentration, it must be used. So which means it must be a reactant. So we have A as a reactant in the forward reaction. In the forward reaction. So which means now what will happen? The forward reaction rate will be having a higher rate than the backward reaction rate. Right? Same thing, I'll explain it in another thing, right? So this is our first example. I am adding extra amounts of A. Let's say I am adding extra C into the system, right? I am adding extra C. So this is the reaction that you need to consider. So when C added, what will happen? The C concentration increases. So therefore, the system tries to decrease the C concentration. So in order to decrease the C concentration, C must be acting as a reactant, right? It must be acting as a reactant. So where do you have C as a reactant? C will be acting as a reactant in the backward reaction rate, in the backward reaction or the reverse reaction, right? It will be acting in the backward reaction. So therefore, what will happen now? The backward reaction rate will be higher than the forward reaction rate. Okay. And let's say the temperature differences or the pressure differences. So the most important one is the pressure differences. As I can remember, there was a reaction, right? So for example, let's say nitrogen plus 3 times hydrogen will give us 4 times ammonia. No, 2 times ammonia. Right? 2 times ammonia. Right. So important fact is that, right? Here you can see there are 4 gas molecules, and here you can see it is 2 molecules, right? So the pressure of a system, the pressure of a gaseous system is directly proportional to the number of gaseous molecules, right? It is directly proportional to the number of gaseous molecules, which means here you can see, here you are dealing with 4 gaseous molecules, here you are dealing with 2 gaseous molecules, which means this side already having a higher pressure, right? Already having a higher pressure, and this side having a low pressure comparatively, right? Comparatively low pressure. The reason pressure is directly proportional to the number of gaseous molecules that you are dealing with, right? It is directly proportional to the number of gaseous molecules that you are dealing with. Right. Now, let's say something like this. I am increasing the pressure over the system, right? I am increasing the pressure. So this is going to be my external effect that I'm going to change in the system. So the system, what will do? So the system will try to decrease the pressure, right? This is the counter effect. So in order to decrease the pressure, you need to choose the side where you have low gas molecules, right? Low gas molecules. The reaction will drive forward that, right? Drive towards that. So here you can see 4 gas molecules against 2 gas molecules, so which means this side is having a low pressure. So therefore, the reaction will go for the side where you have low gas pressure. So therefore, what will happen? The forward reaction rate will be higher than the backward reaction rate. No? It will be higher than the backward reaction rate. So in the other way around, so if I decrease the pressure, so this is the external effect. So therefore, what will happen? The system will try to increase the pressure. So in order to increase the pressure, you need to choose, you need to go forward the side, right? You need to go towards the side where you have higher number of gaseous molecules. So then, according to this, the reaction must go in this direction. So which means the backward reaction rate must be higher than the forward reaction rate, right? So we discussed so many things in the theory classes related to these stuff. So please go through them, right, and try to understand these things. Like you won't be having any sort of calculations related to this, but you will be asked to, like, to determine. So once after we change a factor, what will happen? Whether the reaction is going forward or in the, like, the rate will increase in the forward reaction or in the backward reaction likewise, right? So remember that point. And yeah, then here the Haber process is given. Just go through it, and even in the textbook also we have some sort of small description about it. Just go through it. So the same thing, right? We discussed here N2 plus 3 times H2 having that 2 ammonia molecules. And another thing that I need to emphasize is that, so when it comes to these reaction rates, right? I forgot to mention about the graphs there. Right. Right. So reaction rate graphs, right? Reaction rate graphs. So let's say something like this. Uh, the first one, I'm increasing the surface area. Right? I'm increasing the surface area. So here we are having the rate, and here this is the time, right? This is the time. So let's say in the first instance of, let's say, right, I'll draw a graph like this, right? Okay. So this black colored line, this is for, let's say, um, you are having the reactants, right? You are having the reactants as huge chunks, right? Or we'll say lumps, right? Reactants as huge particles, right? Which means you are having lumps of reactants, right? Guli guli wage tiyena, right? Right. So in order to change the surface area, what should we do? We need to make these particles as smaller ones, right? So whether you can, like, grind it, or you can use dust particles or something like that. You can use granules or something like that, right? So once the granules are being used, right, what will happen is that, so you won't be changing the amount of the product, right? You won't be changing the amount of the product, but the reaction rate will increase, right? Reaction rate will increase. So if we discuss about the rate, so here you will be having the concentration difference over time. So if the rate to be increased, then the taken time, right? The time consumed must be less, right? So if the reaction rate increases, then what will happen? You will be achieving that same amount, but in a less time, right? So this is going to be T2, and this thing going to be T1, right? So T1 is higher than T2. Here, rate 1 is lower than rate 2, right? And this red color line, this will be representing if you are using the reactants as dust or small particles, right? Remember remember this thing, you are having the same amount of the product, right? Same amount of the product. The reason is like in last few years, they asked you to draw these graphs, right? Not so many theory parts, but just asking you to draw the graph and also asking the explanation there, right? So remember this. And let's say something like this. The second one, the temperature, right? Temperature increasing. So still we are having time against rate. So let's say our graph is like this now. Right. Okay, our graph is the initial graph. Let's say T1 temperature graph is like this, and the time taken is T1, simple T1. And if we increase the temperature, so here we are not changing the texture of the molecules or anything like that, texture of the reactants or anything like that, right? The nature of the reactant. But the thing that we are doing is that we are just increasing the temperature of the whole particles, right? Temperature of the whole container. So which means all the molecules will increase their temperature, will result in increasing their kinetic energy. So therefore their speed increases. So you will be having more and more successful collisions. So therefore, what will happen? Still you are getting the same amount of product, but the time taken will be less than the previous case. So you will be having a graph like this. And here this is going to be T2. And here again, T1 will be higher than T2. So this red line refers to T2 temperature, and T2 temperature is higher than T1, right? Still the same amount of products. But there's a special case that you need to remember. It is the concentration change, right? Concentration change. Now you are increasing the concentration, right? So here, time against rate. So we'll say, first, we got the graph like this, right? For a certain molecule, you are having C1 concentration, and this is the T1 temperature. Now, what will happen is that now you are increasing the concentration, right? Which means you are increasing the number of molecules. Okay, get the idea? You are increasing the number of molecules in the system, right? So if you are having more and more molecules, what will happen? You will be getting more and more frequencies, successful collision frequencies, right? So therefore, you will be getting more and more product. For example, let's say something like this, right? You are just reacting three particles against another three particles, right? In the first case. So altogether, you will be getting again three products. But let's imagine something like this, right? Now you are reacting, I don't know, this amount with the same amount of here, right? So each n particle will collide, making a product, right? So here you will be getting a higher number of product, right? I think you got the idea. So therefore, what will happen? Now you will be getting a higher rate as same as a higher product value asset, right? So now the graph might be something like this, right? At a different product level. So I'll write it here. Right, rate 2, or you can say here actually it is not rate, we'll say product. That is much better. Here we are having the product. Here we are having the product. Okay. So this is the C2 concentration, but with the higher product. So remember this, the concentration is the only graph that is going to be changed when we are dealing with temperature and surface area, right? So all the time for the surface area, we'll be having the same product. Temperature, same product. But when it comes to the concentration, you will be having a different product values, right? You will be having a different product values, right? I think you got that point. So if you're fine with it, just react it with a thumbs up, then I can understand it. So this question was given there. You might have seen this question, right? Give me a thumbs up. And if you're having any sort of a question, you can use the chat box. I will answer, right? Okay, good. So remember these points. These are important facts, right? So I'm not going to upload this note in the WhatsApp community. The note where I have written these things. It's better to like making it's better to make your own one, right? So I will be uploading this recording in the YouTube channel as well, on the YouTube channel as well, so you can refer it leisurely. So please make a short note, something like this, right? No need of all the theory parts included. Just draw the diagrams and try to remember them by using the diagrams, right? Okay, so far we have discussed about these things. So yeah, so I have discussed all the stuff that is important here. Yeah, tell me whether you are having any sort of a problems related to this stuff. Any 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 part that I need to discuss. Otherwise, we can wind up the session and we can start at 11 a.m. So there we will be covering two sessions, two lessons, radioactivity and as well as the magnesium part, right? So yeah, tell me whether like are there any questions related to this section? And remember, these are not like these are not like like theory remembering questions or parts, right? Physical chemistry, which means like you need to get more experience in calculating, right? More experience in calculating, and yeah, R1 and R2 is the reaction rate. So remember these. Okay, I will write it here. So normally these symbols, right? So we use these are the standard symbols that we are using. So if it is capital R, this is for the reaction rate, right? Reaction rate. And simple T, most of the time it is going to be time. And capital T, so this is for the Kelvin temperature as well, right? Kelvin temperature or temperature. So these are some standard symbols that we are using in chemistry, right? So here, remember the structures of the graphs, right? Remember the structures of the graphs. Uh, my task thing, right? So go through the tutorials, question tutorials, and please get familiar with the question types that they are going to ask. Okay. And if you're having any sort of questions, just ask, right? You can drop me a WhatsApp message and you can clarify the issues. Right. So I'm going to end the session today for this thing. And tomorrow we'll try to finish all the organic chemistry related stuff, right? And yeah, at 11 a.m. we'll start the physics session as it, right? And yeah, uh, R2. Yeah. So here, the time taken is less than Sadhan, right? So as I mentioned here, see, the rate is equal to the concentration difference divided by the time, right? If the rate is higher, then the time consumed will be lower, right? Just imagine something like this. You are getting some sort of a product within minute, right? So we'll say that is R1 reaction rate. Within a minute, you are getting, let's say, 5 moles of something. But just imagine there's another reaction which provides you with the same amount of 5 moles, but within few seconds, then the time consumed is less, right? The time consumed is less. So therefore, the reaction rate is higher. The reaction is occurring at a huge speed. So if the speed is higher, the time taken is lower, right? So that is the reason here. See, same product observed, right? Same amount of the product observed, but in different time frames, right? So T1 is the higher value here, right? T1 is the higher value. T2 is the lower value. So if the time taken is higher, then the rate is lower. Okay? Then the rate is lower. Right. So I'm going to end the session now. Uh, at 11 a.m. We'll start the magnetism and the particles related discussions as well, right? So please go through them, and I feel like it's better to focus on this graph thing, right? So there were so many questions. Go through the question tutorials as well, right? Okay, so I will be ending the session. Hope to see you at the 11 a.m. session as well. So in that session, as I mentioned, I will be covering two sessions there, two topics there, right? So better to join it. And you can find this video on the YouTube channel, right? So please go to the YouTube channel. It might be on the section where I upload the normal video. So under the live session, I can't remember where I uploaded it. So never mind, right? So please go through it, and yeah, you can refer it until the exams are done, right? Okay. So thank you for joining, and we'll hope to yeah, we'll do